So this is fourth chapter, which is on generative adversarial networks, and probably most of you have heard of it. This is still something people use. One of the first, I would say, ideas which work quite well, and you didn't really need to go through all of those complications that we have for explicit distribution learning. And this chapter is going to be quite short as compared to the other chapters because GAN idea, I mean, it's simple. At the same time, there are a few things in it which you really need to know. The rest of it is just a basic, implementational extensions. So let's just have first a quick recap on the ideas that we are going to meet from now on in the remaining chapters. So these ideas are what I call them, like you can call them modern data generation or implicit data generation. So the key point here in these ideas is that, as I told you, we're not going to insist on this fact that we want to know what is the distribution itself. We want to know how we can sample from that distribution. If it ends up with knowing the distribution, that's OK. But we necessarily do not need to know that. Yeah? So this is the idea of modern generation. So you start from one distribution. Now, I mean, initially in chapter 2, when I showed you this diagram, you didn't know what is this z, right? But now you know that this is essentially your latent variable, right? So it's exactly like what we did in flow networks. You have this latent variable. Then you're going to pass it through one generator. And this generator is going to give you your sample. Now, you might tell me, so what is the difference with flow? But in flow networks, we had this extreme restriction. It should be deterministic function and invertible, right? But I can put this g to be anything, right? It could be deterministic, non-invertible. It could be even stochastic, right? So if you remember in Langevin dynamics, we were just processing something randomly, right? Adding up Gaussian noise to it. And it can somehow be included inside this generative model. This is, for instance, what we do in the diffusion models, right? So this generator does not need to be deterministic, does not need to be invertible anymore. And the only thing that we can do, we can sample from this distribution. And typically, it's very hard to understand what is exactly the distribution of the output. But maybe we can guarantee that whatever that guy is looking like the data distribution. So this is what we do by maximum likelihood. But sometimes we cannot do exactly the maximum likelihood. We do it somehow implicitly, indirectly. And you're going to see the first example here in GAN. Once we have done the training with this either explicit or implicit maximum likelihood, we're going to use that network for generation, right? So again, that network is really now looking like a black box for us because sometimes we even don't have idea what is the distribution coming out of it, but we know that this is looking like the data distribution, right? OK, so that is a high-level idea that is going to be with us for the rest of semester. And then let's start with the first one, which is the GAN idea. So I told you initially in last chapter that latent space is actually somehow trying to represent the data manifold, right? And you do know that data manifold is much lower in dimension, right? So if you have one image, one MNIST image, you can sometimes represent it with a latent variable, which is as small as 8-dimensional, right? And this means that this huge MNIST image could be represented with only 8 entries, right? So 8-dimensional space is being converted to 784-dimensional space, right? So your latent dimension could be significantly smaller. But in the flow-based networks, which was the first kind of network we started working with latent space, we were not able to use this property because essentially we needed this network to be invertible, right? Now, one thing that we have intuitively in mind is that even though we could not do it there, it should be somehow intuitively rational that we can generate everything from much smaller space, right? If I can compress any MNIST image into 8-dimensional space, then it makes sense that if I sample from that 8-dimensional space and I pass it through one good decompression operation, I'm going to end up with the kind of sample that I'm looking for, right? So this makes sense, but we could not do it up to this point, right? Now, you might ask me this question, okay, why this is a big deal? Just put one function, one network, which takes something small dimensional, and then make it high dimensional, and then try to train it, right? So you might come with this idea, but the issue is that when you think like this, if you want to do the training following the general recipe we have, the maximum likelihood, we're going to get into trouble. And we're going to take a look at the particular examples where, I mean, like in this GAN case, we cannot really do it, okay? Now, let's just formulate everything that we want to do here. So now we want to have a generator model. So this generator model is any model that is taking some sample noise or sample latent variable here, which is generally m-dimensional. It doesn't need to be d-dimensional anymore. It's coming from as small as one-dimensional space, and then it's going to pass it to the data space. And I assume, again, that the data is continuous in the entries, because that is going to be easy for us in terms of analysis. And whenever we have a discrete, like real images with discrete pixels, then we can think of them as quantized version of this guy. So I have m-dimensional latent space. I want to convert it into d-dimensional, and I have this generator model, right? This is the most generic thing I can think of. This guy, we typically assume that this guy in the latent space has a kind of distribution. This is an easy-to-sample distribution, exactly like flow-based models. And this whole generation process is going to convert it into the data sample. The sample which is somehow distributed with your data distribution. Now, you might tell me this is flow. I think I made it clear in the previous slide for you that this is not necessarily flow, right? Because neither this guy is needed to be invertible, nor it's needed to be deterministic. So again, this G could contain some random process as well, right? So it might be some random things generated in between added to your input, right? This could happen as well. Now, sampling from this guy, again, easy as before, right? So you just sample latent space, easy. You pass it through G. As long as G can do the process, can go forward, everything is fine. So that is no problem. But the whole issue is that what if we want to train such an architecture? What if we want to train this generator, and now we have this constraint that this is not anymore invertible, right? Now, at this point, let us first focus, just for simplicity, let us focus on the case where this G is just a neural network, meaning that there is no random process involved. So it's essentially the flow-based models that we had before, but this time this is non-invertible, okay? And now what I want to do, I want to repeat what we did in the flow-based models. So we started from one distribution in the latent, and then we computed by change of variable the distribution of the output, right? So I want to do the same thing, but this time I do not assume G to be invertible, okay? So let's do it together. Say sample X is the output of the generator, and Z is distributed with the distribution Q. Now I want to compute the distribution of X, which is this output. What should I do first? Do you remember how we did it in the flow-based networks? When we wanted to compute the distribution of the output, what did we do first? Yeah, that's fine. Yeah, that's correct. But how did we do the computation? Like, how did we characterize the output distribution? You remember? We first computed the CDF, right? Yes. CDF. We computed the CDF. And then after computing the CDF, we take the derivative of the CDF. It was the distribution of the output, right? So we can do the same thing here. Everybody's clear what I'm doing? Yes? But now I'm not thinking of one-dimensional to one-dimensional anymore, because I don't want to have that. It's non-invertible, right? So I assume m-dimensional to d-dimensional, right? But again, you can do it the same way, right? So you're going to write down the probability of this GZ, this generative output, GZ, to be smaller than one particular point X. And this X could have d different dimensions, right? G has also d different dimensions. This means that first dimension of G should be smaller than the first dimension of X. Second dimension of G, Z, should be smaller than second dimension of X, and so on, right? If I can compute this guy using the distribution of Z, this Q distribution, then I have the cumulative distribution function. I'm going to take the derivative with respect to all variables here, right? X1, X2 to Xd. This is going to give me the distribution. This is what I want, right? I need to have this, then I'm going to put the samples inside it. I compute the likelihood. I maximize the likelihood. Story is over, right? So I need to do that. I require that particular distribution, right? So let's do it together. How can I do it? Of course, the function is not invertible, so I cannot really do that easy thing as before. So I say like X is smaller, G of X, Z is smaller than something. It means that Z is smaller than the inverse of the G at that thing, right? So you cannot do this anymore, right? And I'm going to give you one particular example to make it clear why you cannot do it. It's not really the case, because when your G is smaller than something, there is no need for your Z to be exactly smaller than something else, right? Just, where is the check? Okay. Z squared, G of Z, equal by Z squared. Smaller than or equal by 1. Does it mean that Z is smaller than something only? No. This means that Z is between 1 and minus 1. So Z cannot be smaller than minus 1 as well, right? What if I write it down GZ equal by minus Z squared? Then what's going to be, GZ is minus Z squared is smaller than 1. If you want this happen, what should happen? Z squared should be more than or equal by here should be minus 1, minus 1, okay? So Z squared should be more than 1, right? Correct? And then what is the region that this is happening? Either Z is greater than 1 or Z is smaller than minus 1, right? So there is no reason when GZ is smaller than something, when G is not invertible, when GZ is smaller than something, then necessarily Z is smaller than something else or more than something else. This is not happening. It could be in some specific region. That region could be compact. It could be disjoint like the second one, right? So you have two disjoint sets together, right? Both of them are satisfying the condition. So there is no need for this guy to be of an easy form, and the only way that I can deal with it is that I define it as a kind of set. So I'm going to define the set ZW. This depends on my model because G is involved here. At the particular point X to be the region where this G guy, this generator output, is smaller than X. Okay? So any point in the space of Z which is satisfying this condition is inside this set. Clear? Now, say I have this set. How can I compute the CDF? You're going to integrate the Q distribution. Exactly. You're going to integrate the Q distribution. Oh, this should be Q, sorry. Not PZ, QZ, because distribution of Z is Q. So I'm going to integrate QZ, the distribution of Z, exactly on that set, right? So wherever I see that this condition could happen, I should integrate my distribution at that part, right? And this is going to give me the CDF of X. Once I have this guy, I can compute the distribution by derivative, right? Everybody's cool? So the distribution is going to be the derivative of that expression that I showed you. And now, if you want to take the derivative, you need to take the derivative with respect to X, right? Where is X showing up in this expression, the thing that is under the derivative? Inside Z, right? So it means that you need to take the derivative essentially from the guy here, right? If you do chain rule, then this is going to show up, right? But the problem is that you don't really know what that guy is. That guy could be super complicated, could extremely change from one point to another. Yeah? So this is a very challenging computation. And I I hope that you're seeing it right now, but if you don't see it, let me just give you one example. So you might tell me that, okay, you just want to do chain rule. Basically, you just take the derivative of this guy with respect to anything sitting here times the derivative of this set z with respect to x. But as I told you, when z is not invertible, then the issue is that you cannot specify z set that easy. And I'm going to show you in one example. So one thing that I want to mention again here, just to recap what we did in the previous chapter. In the previous chapter, we also had z, but I didn't mention it for you. Because that z was quite easy. Since the function is invertible, if I want to know where are the points where g itself is smaller than x, I need to find all points u which are smaller than x, and then I compute the inverse of those points, right? That is the same thing because I know that I have the inverse transform. And because of that, we had no problem. We ended up with the normalizing flow expression that was making life easier for us, right? But here we don't have it. Everybody's cool? Yeah? Okay, so let's take a look at one example to make things clear. So say my generator is this guy, okay? And here there is no weight involved, just a deterministic function g defined in terms of z. So it's going to get z, which is one-dimensional. It's going to map it into a three-dimensional x. And now the first entry in this gz is minus z squared. The second one is exponential of minus z. The last one is z itself, right? So you get z, you compute a three-dimensional vector, right? That's it. And now you're just sampling z from one distribution. You want to know what is the distribution of the output, right? If you want to do it, essentially, you need to just compute that z matrix, the z set, right? And this means that, okay, let's say my x, I'm looking at one particular point, x1, x2, x3. So this is one point in the three-dimensional space. And what I want to do, I want to compute the set z at that particular point, x, right? So I'm going to write it down. So set z is essentially a set of all real values whose generator, gz, is smaller than x, right? And you can just open it up, make it easier. So it means that the first entry of your generator is smaller than x1. Second entry of your generator is smaller than x2. Third entry of the generator is smaller than x3, right? Okay, so you need to find the set of values for z, the real values, which satisfy all the three constraints, right? Okay, so let's write down the first constraint. The first constraint says that minus z squared should be smaller than x1, right? This means that z squared should be more than minus x1, right? And then what are the points which satisfy this condition? I mean, assume that x1 is no negative, okay? So that minus x1 is positive. Which points have this property? It should be either more than square root of minus x1 or less than minus the square root of x1, right? Exactly like this example we had on the board, right? You want z to be more than 1. Say x1 is minus 1. You want z to be more than 1. It should be either, z itself should be either more than 1 or it should be less than minus 1, right? Because minus 2 squared is also 4, right? It's more than 1. Everybody's clear? So the set which is satisfying this condition, I can write it down here because we're going to use it later. So the set that is satisfying this condition is this one. So this is the set, the z-axis, so the real axis. Here is 0. Here is minus x1 square root. Here is minus the square root of minus x1. So this part and this part. Any points on these two parts is going to satisfy that condition, right? Clear. Okay, let's go now for the second one. What is the second condition? The second condition that the exponential should be less than x2. This means that the logarithm could be taken from both sides. So minus z should be less than logarithm of x2, or z should be itself more than minus logarithm of x2, right? So again, you're going to have something. So for instance, say that this is here. Say this is the point where minus this is minus logarithm of x 2. And then any point above that is going to satisfy this condition, right? Now, if you want to combine this guy with the previous one, what's going to happen? So you're not going to have these guys anymore, right? Anything here or anything here is going to still satisfy what you want, right? So this is going to be your z set up to this point. And the last thing is the third constraint, which itself is already well formed, right? Z should be smaller than x3. So if you assume, for instance, x3 is here, say x3 is here, the value, then this guy should be smaller than that, right? And then again, you're going to say that, okay, the overall set, valid set, going to be this part and this part, right? Everybody's cool? Questions? Okay, so that set Z, you can now write it down, right? So it's going to be the set which is satisfying the first constraint, overlap with the set that is satisfying the second constraint, is overlap with the set that is satisfying the third constraint, right? This is going to be the set that is valid. And you need to integrate Q over this set in order to get your distribution, right? Everybody's cool? Okay, now let me just give you a few examples. So say that my x is this one, okay? Minus 1, x of 2, and 2, okay? If you put it inside that expression I found you, so minus 1 after x1 is minus 1, so it's going to be minus infinity to minus 1 and 1 to plus infinity. This is the set. This is exactly what I showed you here. So here the guy is 1 minus 1, right? So 1 minus 1. The second one is exponential of 2, so minus log of x2 is going to be minus 2, right? So this guy here is going to be minus 2. And then the last one is 2 itself, so x3 itself is going to be 2, right? Meaning that the set of valid points here is going to be between minus 2 and minus 1, and 1 and 2, right? So this set, this one, and this one, right? Okay, that's fine. So you can compute the CDF over this guy. But what if, for example, I have this one now? What if x2 is 1? What's going to happen? If x2 is 1, then logarithm of 1 is going to be 0, right? Then when you look at this thing that we have on the board, this minus 2 is going to shift here to 0, right? Meaning that no negative point can be considered anymore, right? So our set is going to be only 1 and 2, right? So we had 2 disjoint sets before. Now we have just 1 set, right? And what if I put x1, the first entry, to be anything positive? Then what's going to happen? There is no point that satisfies that condition, right? So the set is going to be empty. Clear? Now, what you can see, I mean, if I want to, for instance, use this formula, this z term that I have here to compute the CDF, I'm going to end up with a CDF whose expression is going to change from one x point in 3 dimensions to another, right? And it's not changing only like the value of the function. The whole function could change, right? For instance, in the points that I showed you, if I have my first x, it's going to be sum of 2 integrals, right? If I have my second x, I'm going to have just 1 integral. If I have my third x, it's going to be 0, right? And you can come up with lots of other points, right? Lots of other points which have different forms, right? Moral of the story, this is quite hard to analytically specify this CDF. And because you cannot do it, you essentially cannot compute the derivative to end up with the distribution. Okay? So, moral of the story here is that this z set is quite hard to be, when your function is not invertible, this is very hard to be specified, and because of that, the distribution itself is very hard to be specified for a general point x, and due to that, you're going to have trouble for training. What is the trouble for training? What if you want to train this generator? What should you do? I'm going to give you a bunch of points from the data set, right? what do you need to do with those points? You need to likelihood, right? You need to compute likelihood, right? And then you need to know what is the distribution. This means that you're going to put that particular point in the distribution PW, compute it, and try to maximize it over W, right? So if you want to train generator with maximum likelihood, you need to compute the likelihood for all the samples that you have in this form. But the whole issue is that that guy is very hard to be computed for every single point, right? There is no generic form like what we had in the normalizing flow to compute that, right? If you really want to do it, you really need to know what is your data point, right? So for every single point, you need to go after that set Z, find it, compute the integral, which is not impossible, but you can imagine how nightmare that is, right? It's pretty much, technically it's impossible, right? So moral of the story, likelihood in this case is not directly computable. And this is why we insisted on having invertible transform in the flow-based networks, because that is the only way we can compute the likelihood feasibly. Okay? Now, what can we do if we don't have a feasible likelihood? Yeah. So this is the point that people at some point were somehow thinking, and they said, okay, we should not do anything else. We should stick to that, kind of latent space that we are thinking of, same dimension, right? We always need to work with likelihood, right? But the point is that there was one intuitive idea, which is the GAN, and then when people did this, they saw that it's really working, and later they saw that it is implicitly computing the likelihood, not explicitly, okay? So let me just explain the idea, and then we're going to get into the training and the other thing next session. So what is the idea of GAN? The idea is, the root idea is very intuitive. It doesn't have yet anything with likelihood or something like that. So it says that the guy here is the generator, and this guy is going to generate some sample from a distribution and convert it into what I want, right? Now, this thing that comes out of it is a kind of fake example of the data, right? This is something that the generator tries to fake, right? And now, if I cannot compute the likelihood, maybe I can just put something here to judge whether this is really looking like the real data or not. This is what we call a discriminator. So we're going to put one discriminator here. What is discriminator? Discriminator is going to look at your generated sample and going to tell you whether this is a real sample or a fake sample. So the task that discriminator is doing, what is it? Classification, exactly. It's just doing classification, fake or real, right? Now, if it wants to learn how to classify, it needs samples, right? What are the samples for the fake image or fake sample data? Coming from the generator, right? So generated samples by this guy, so I just sample lots of noise. Each time I pass it through this generator, I'm going to get some fake data, right? And now, do I have any data with label real? Do I have it as well? The data set, right? So I'm going to feed the data set as well. So the data set also contains data which are labeled as real because they are the real samples. And then I train my discriminator on this classifier to just understand how it can distinguish between real and fake image, right? Everybody's clear? Okay. Now, if I can make a mechanism that once I am training this guy, I also give some information backward to the generator to tell him, okay, look, I am finding out 80% of your fake images, right? Then it's going to change those weights with respect to this number, 80%, such that it can next time make this 80% 70%, right? Next time 60%, and so, right? So if I can make a mechanism to just send back some information to this guy, to this generator, so that each time it sees that information, it can improve its weights in the sense that the discriminator is going to get more and more confused next time, then I am able to train that generator even without having the likelihood, right? Everybody's cool? Everybody got the idea of GAN? What it's doing? Now, one question, and don't panic if you don't know the answer. Just want to test whether you got the idea up to this point. What kind of thing going to go backward here? What kind of information going to pass here? Just guess. Don't be shy. If you say it wrong, no worries. It's empirical risk, but not empirical risk itself, something else. Yeah, cross entropy, you use it to compute that empirical risk. But what you pass, gradient. Great, okay, you see it. So this gray guy should be a form of gradient. Yeah, you might guess, but if you don't see it immediately, that's totally fine. We're gonna do it together, okay?